Hey folks, welcome back to our third and last video on Unit V, this short little unit on the population variance. And then after that we'll get into really 307 proper. So it's taken us a while to get there, but there were some really important building blocks that we needed to get there. So let's take a look here at, let's see, this is on page V7. So we've taken a look at the chi-square distribution, and we've looked at how to do a hypothesis test for sigma squared or sigma, and we looked at it as both a classical approach and a p-value approach. So the last piece that we want to look at here is how do you do a confidence interval for sigma squared or for sigma, same kind of animal here. One thing I want you to note is, let's go back and take a look at when we did a hypothesis, or sorry, a confidence interval for mu. And what we had in that case then was we had a z or a t, and then we had an x bar minus mu. Wouldn't be a mu naught there, it would be just a mu, because it's not a hypothesized value. And what we could do is we could isolate this particular guy here and solve for mu, and we end up with something that looks like this. We would say it would be an x bar value plus or minus a z value based on alpha over 2 times sigma over the root of n. And of course that could change if it's a t distribution, and you'd use s, and there could be an FPC factor, the same kind of stuff that we talked before. But the important thing I want you to note here is that this is an x bar plus or minus a margin of error that looks like this. And so it's plus or minus, and it would be the same amount on both sides, because this z value would be either a positive or a negative value, such as 1.96 or minus 1.96 if it's a 95% level of confidence. The important thing to note about the confidence interval for sigma squared here is that the formula is different. It looks like this, and so we would be solving for this guy here. And so you end up with, if you isolate this, you basically, this goes up and this goes down, and then you come up with this, and you end up with a lower and an upper tail value, but it's not like an x bar plus or minus a margin of error. It's not the equivalent of an s squared plus or minus a margin of error, where the margin of error is the same on both sides, because it's not a symmetric distribution. Remember, a chi-square distribution is skewed. And so it's you actually have to calculate two different values here. Now you still got margin of error here in terms of one's higher than the s squared value, one's lower than the s squared value, but the distance won't be exactly the same, because it's not a symmetric distribution about zero. It's a skewed distribution around the degrees of freedom. So what we have down here is, instead of having a plus and minus z value, you have a chi-square value, which is based on alpha over 2 in the upper tail, and really alpha over 2 in the lower tail, which would be 1 minus alpha over 2 going up, using the convention that we learned back on page V3. And then your degrees of freedom. So it's similar in that way to a t, in that it's got an alpha over 2 and an n minus 1 degrees of freedom, but you'll have to look at two different columns on a chi-square table, because it's not symmetric. So this is what we end up with, is our confidence interval looks like this here. So we just need to find the lower bound and the upper bound, and then put it into the formula like this. So let's go and do that. Just one thing I want you to note here is, let's take a look at a chi-square table here, or a distribution here, and you can think of 95% in the middle here, And so that would leave us with 2.5% on each side. So we want to find out what are those chi-square values that we can use that go into these spots here. Now, this one here actually then is the 1 minus alpha over 2 value, and then n minus 1 degrees of freedom. So that would be chi-square 0.975. All that means is you've got, if you got 2.5% below, you've got 97.5% above. And then this one here would be the upper value. This would be the 0.025, and then n minus 1. So that would be the 2.5% in the upper tail. Now, when you take a look at this here, it looks like they've been switched, and they actually have. You know, this is actually the bigger number, and this is the smaller number. This came from the right-hand side of the table. This came from the left-hand side of the table. But remember, if you have a bigger number in the denominator, then this whole thing becomes smaller. And you got a smaller number here, this whole thing will be bigger. And so that's how that works. People sometimes get kind of confused about the notations and about, well, you know, which side does it go on? And the point is that it doesn't really matter. You take your alpha, you split it in half, you go and you take a look at the chi-square table for alpha over 2 in the upper tail, alpha over 2 in the lower tail. You stick it into the formula, and one of the numbers that you end up with as an answer is going to be a bigger number than the other one, and then you just simply write it that way, with the smaller number on the left and the bigger number on the right. So don't get hung up if you put the wrong one in the wrong spot and so on like that. Let's take a look here, and I'll show you practically how we do this. So let's find the 95% confidence interval for the sigma squared in the Army recruitment example. Just to remind you, this was an n of 30, and we had an s squared equal to 18. And that's going back up here to the original problem right there. Okay, so there's the 18, and there is our n of 30. And we're going to use an alpha of 5%. Actually, it tells our level of confidence down here anyway, so we're looking at a 95% level of confidence. So alpha will be equal to 0.05, and alpha over 2 would be 0.025. All right, so what we need to find out then is these two guys here. n minus 1 times s squared over sigma squared, and this would be the 0.975 value, 29, or if you like, this is something you can do. You could say 2.5% going that way, and then 2.5% going that way. The upper tail and the lower tail, like that. All right. And having said all that, did I put those backwards? Yeah, no, I'm good. And this is, no, I did. Yeah, you see how easy it is to get messed up there? So on. So let me back up here. And the thing to note here is don't get hung up on that. So this is actually the 0.025 value going up, and then this is going to be the 0.025 value going down, which is the 0.975 value going up. That's 1 minus alpha over 2. Again, you just find the two numbers, you stick them in, and then you're going to end up with a bigger number and a lower number as an answer, and that's how you do that. Let's go and find these two guys here. So we're going to go to 29 degrees of freedom. Is that right? Yeah. That's n minus 1. So that's our n minus 1. And we'll go to page 221. And let's just clean this up just a little bit here. All right, so 29 degrees of freedom, and all we do is we go to the 2.5% column going down, which would be this guy right here, 16.0, and then the 2.5% column going up, and that's going to be this guy right here, 47.5. Just going to check my notes here and make sure that I got those right numbers there. Okay, and so that's how we do that. I guess I can get rid of these two guys there. So 16 and 45.7. All right, so what we'll have here then is this will be 30 minus 1 times 18. The 18, remember, is already squared. And then down here, this is where we put really the bigger number, 47.5. So that was the 2.5% going up. And then we're going to have 30 minus 1 times 18 over 16.0. That's the smaller number. And that's the 2.5% going down. And when you figure those numbers out, you're going to get 11.4 and 32.4. And remember, if you got the numbers in the wrong denominator and so like that, and you had them switched, don't worry, one's going to be a smaller number, one's going to be a larger number, so you just simply put the smaller number here and the larger number here, and there's your answer. That's it. Remember that we are looking for a confidence interval for sigma squared. If I was to ask you for a confidence interval for a sigma, the last thing that you would need to do is to take the square root of those. So it would be the square root of 11.4 is less than sigma is less than the square root of 32.4 is equal to 0.95. But in this case, we're asked for a confidence interval for sigma squared, the variance, and so that is the n there. All right, that leaves us with this problem here. So I'd like you to do this one. By the way, this has got some really small numbers. Like we end up, for instance, when we get into the confidence interval, it's 0.00008. So you can't really take it to 2 decimal places. You'll have to take it to about 5 decimal places before you even get a meaningful number there on that. But we're going to do the confidence interval here, and then we're going to do a hypothesis test here by using both a classical approach and then a p-value approach. I'm going to leave those for homework. Just want to remind you that at the end of the unit, and from this point forward then, you'll see that there are additional problems at the end of each unit. So unit V has a bunch of problems here, and then there's solutions right here. And so remember, don't just passively read the problem and look at the solution. Read the problem, try it out, and then check out the solution. That's how you're going to learn. So that will take us to the end of the unit, and of course the end of this particular video. Talk to you later. Thanks for listening.